In section 5.4, we're not really learning any new content. We're just putting together what we've learned in this unit and in past units in some common themes that we see that come up with table problems. So some of this is from Unit 5, some is review, but none of it is brand new in section 5.4. So in this first example on page 80, we're given a differentiable function f, and we are given just some values of f in a table. And we are asked to use a left-hand Riemann sum with intervals indicated by the data to approximate the definite integral of f from 0 to 6. So when this says intervals indicated by the data, we just use the intervals that are given to us in the table. So when we're doing a table problem like this, I always like to sketch my rectangles on top. So I'm going to go from 0 to 1, then from 1 to 2, 2 to 3, 3 to 4, 4 to 5, and 5 to 6. So we have 6 rectangles that we're going to use, 6 subintervals. It just so happens that for all of them, delta x is 1, but we need to be careful because that is not always the case. So if we are doing a left-hand Riemann sum, that means for each rectangle, we need the value on the left. So I like to put a little dot on the left side of each rectangle. So for my first rectangle, the dot is going to be at f of 0. Then that's the left-hand side of my second rectangle, my third, my fourth, my fifth, and my sixth. Okay, so when we do the left-hand Riemann sum, we know it's an approximation, so I'll use my approximately equal to symbols. Remember that we've got to show in our work a product and a sum. So what I like to do first is write in like f of 0 instead of just plugging in that 3. So I'm going to multiply the left-hand side of my first rectangle with the base of the rectangle, which is my delta x. So my delta x for each of these is going to be 1. But like we said, that's not always the case. So f of 0 times 1 gives us the first area, plus f of 1 times 1 gives us the second area, plus f of 2 times 1, plus f of 3 times 1, plus f of 4 times 1, plus f of 5 times 1. Remember, we don't add f of 6 times 1 because that's the right-hand side of our last rectangle. So we have 6 rectangles, we only want the left-hand side multiplied. So now if we go back and we plug in for f of 0, f of 1, etc., if we plug in the actual values for our table, so this is 3 times 1, 7 times 1, 6 times 1, 4 times 1, 1 times 1, and 2 times 1. And then we just add those up. So 10 plus 10 plus 3, we should get 23. And since we don't have any like units for f, it's just some function, we're not going to worry about units. In part B, we're now asked to use a midpoint approximation, and we're going to use 3 subintervals of equal length. So again, when they're of equal length, that means our delta x's will be the same, or will be equal. So remember that to figure out the length of our subinterval, when we're told to use 3 subintervals of equal length, is I'm going to, so it's supposed to be an arrow. So I'm going to plug in 6 and 0 for B and A respectively, and divide by the number of subintervals. So 6 over 3 is 2. So my delta x for each subinterval will be 2. Instead of erasing my table, we usually don't do more than one Riemann sum in a particular problem. I'm going to re-sketch just the x part of the table down here. So that's for x equals 0, 1, 2, 3, 4, 5, 6. If we are doing a midpoint approximation with 3 subintervals where delta x is 2, I need to start at 0, add 2 to that number, and that's the boundary of my first rectangle. Then starting at 2, add 2 to that number, that brings me to 4. Starting at 4, add 2 to that number, that brings me to 6. So remember, when we're doing a midpoint approximation, I don't want to use the endpoints of the rectangle, but the midpoint. So the midpoint between 0 and 2 is 1. The midpoint between 2 and 4 is 3. And the midpoint between 4 and 5 is 6. So that means I'm going to be using f of 1, f of 3, and f of 5 to represent the heights of the 3 rectangles respectively. So our definite integral of f from 0 to 6 using the midpoint approximation, well, it's going to be approximately f of 1 times, now remember, my delta x is not 1, but rather my delta x for each of these rectangles is 2. So the area I'm calculating is f of 1, the height of the rectangle, times 2, the width of the rectangle. Then I'm going to add f of 3 times my delta x of 2, and then we're going to add f of 5 times our delta x of 2. Okay, so if I plug in the values from the table, f of 1 is 7, f of 3 is 4, f of 5 is 2. So 14 plus 8 plus 4 is what? 18 plus 8, 26. So our midpoint approximation yields 26. Okay, parts C, D, and E are not Unit 5 problems. These are some throwback table problems. So in part C, we are asked to estimate the derivative f of 2.5 using the data in the table. So remember, we can estimate an instantaneous rate of change by using the average rate of change. So the closest average rate of change of f that we could get, since we know 2.5 is between 2 and 3, we could find the average rate of change of f on the interval from 2 to 3. All right, so if we just substitute in the values that we have in the table, that is 4 minus 6 over 3 minus 2, which is 1. So we get negative 2. So again, we can approximate or estimate the instantaneous rate of change of f at 2.5, which is the derivative, by using the average rate of change on the tightest interval we can fit around 2.5. In part D, we're just asked to find the average rate of change of f on the interval 0 to 6. So we know that's f of 6 minus f of 0 over 6 minus 0. So 4 minus 3 over 6. So we get 1/6. All right, lastly, in part E, must there be a C on the interval from 3 to 6 where f has a horizontal tangent line? Justify your answer. Well, we know that f would have a horizontal tangent line where the derivative equals 0. So I need to connect those ideas. So if f has a horizontal tangent line, that means f prime is 0, since the slope of a horizontal line must be 0. So what this problem is really asking me is, must there be a C on the interval 3 to 6 such that f prime of C equals 0? And that should tell me that this is a mean value theorem problem. So we can only apply the mean value theorem if the function is continuous on the closed interval 3 to 6 and differentiable on the open interval. So going up to our problem, we were told that f is a differentiable function. So down here, I need to communicate that because f is differentiable, therefore f, or thereby f, is continuous. Okay, so that satisfies the hypothesis of the mean value theorem. So going back to part E, must there be a C? Well, the mean value theorem tells us that yes, there must be a C if the average rate of change over that interval gives us 0, then there must be a place where the instantaneous rate of change is 0. So let's find the average rate of change. And that's going to be from our table 4 minus 4 over 3, which is 0. So to answer the question, the MVT does not guarantee us a horizontal tangent line. Instead, the MVT, the mean value theorem, guarantees a C on the interval from 3 to 6 such that f prime of C equals 0. Therefore, f must have a horizontal tangent line at x equals c. So whatever value of x that is, that's where the tangent line must be horizontal. So that is a mean value theorem question, but we need to make sure we connect that idea that the derivative equals 0. That's where f has a horizontal tangent line. All right, question or the example on page 81, we've got another table problem, but this time we're working with a rate in context. So let's be careful that we decode this prompt. So the rate at which the temperature fluctuates over a 12-hour period is represented by a differentiable function r of t, where r is measured in degrees Fahrenheit per hour. So r is the rate at which the temperature fluctuates, and the units are degrees Fahrenheit per hour. So r is the rate of change. T, our other variable for time, represents the temperature in degrees. And we can sort of infer that, but we're giving it right there, degrees. And then we are told that the temperature at time t equals 0 is 72. So just be careful. This is not r of 0. This is some other variable that represents the temperature. In part A, we can see in the table that r of 2 equals negative 1.3. Explain what that tells us about the temperature. So when we answer in context, remember that r is the rate at which the temperature fluctuates, and t is a time. So at t equals 2 hours, the rate at which the temperature fluctuates is negative 1.3 degrees Fahrenheit per hour. So don't forget your units, hours, and degrees Fahrenheit per hour. And don't forget to interpret that in context. In part B, estimate r prime of 7 and explain what this tells about the temperature. So when we estimate the derivative, we use the average rate of change of r to estimate the instantaneous rate of change. So since 7 is between 6 and 8, r prime of 7 is approximately the average rate of change of r over the interval 6 to 8. Okay, so when we show our work, don't forget that difference quotient. And we should get -1/10. So to explain that in context, remember that this is an approximation. So we would say at t equals 7 hours, the rate at which temperature fluctuates, so that's R. Oops, it's hard to write. Remember, we're explaining how R is changing in an instant. So at t equals 7 hours, the rate at which temperature fluctuates is, and we could say changing or decreasing. I'm going to say decreasing since it's negative. All right, is decreasing by approximately 1/10 degree Fahrenheit per hour squared. So don't forget our units. If R is measured in degree Fahrenheit per hour and T, time, is measured in hours, if we take the rate of change of R, remember that's going to be our R units divided by our T units. So degrees Fahrenheit per hour divided by hours. So that's degrees Fahrenheit per hour, or per hour squared. Okay, in part C, we're asked to use a right-hand Riemann sum with 6 subintervals indicated by the table to approximate this definite integral. So if I go up to my table, my subintervals indicated by the table, I just use the data in the table. You got to be careful though, because delta t is not consistent. So delta t is 2, then 1, then 3. So from 6 to 8, that's a change of 2, 8 to 9, a change of 1, and 9 to 12, a change of 3. So I like to write those above my rectangles. And then we are using a right-hand Riemann sum. So that means I'm going to use the right-hand value of each rectangle. Okay, so when we approximate our sum, I'm going to use the right-hand side of each rectangle, and that's going to go with the delta t above it. So I'm going to multiply r of 2 times 2 plus my next right-hand side is r of 3 and times the delta t of 1. My next rectangle is going to be r of 6 times delta t of 3, then r of 8 times 2, because that's the change from 6 to 8. The next rectangle is 1 unit wide, so r of 9 times 1, and then lastly, r of 12 times 3. That's my last one. Okay, so when we plug that in, we just got to do this calculation carefully. All right, I paused recording just to fill that in so you didn't have to watch me write. Lastly, we just do the multiplication and then add up those different terms. And I believe we should get 12.9 for our approximation. We should be able to do this without a calculator, but sometimes for the examples, I just punch them in the calculator because it's tedious. All right, in part D, we are using the trapezoidal approximation with 2 subintervals to approximate the temperature at time t equals 3. So let's think about what that means. We don't have a variable for temperature, but if R is the rate at which temperature changes, I could define a new variable to be the temperature at time t in degrees Fahrenheit. So that means the rate at which uppercase T changes, that is our R of T. So we could write an accumulation function to help us. I might just somewhere, I know I wrote it up above, I would show that I'm using this new function that I made T, and I would say that T is temperature at time T. And if we write an accumulation function for the temperature at any given time, we always have to have a known, like a known temperature. So we were told in the problem that the temperature at 0 is 72. So that means T of 0 is 72 degrees. So for our accumulation function, I use my known information here. Whatever T value this has to be the same. This is our variable T. And then now when I write my definite integral, I use a dummy variable. Okay, so if we are asked to approximate the temperature at time T equals 3, I know that's going to be 72 degrees plus the definite integral from 0 to 3. So when I'm using a trapezoidal approximation, this is what I am approximating. So if I look at my table again, I'm just going to re-sketch it because I only need my table from 0 to 3, and my t values were 0, 2, and 3. So when I use a trapezoidal approximation with two subintervals from 0 to 3, this is one of them, and this is the other. And again, we have to pay attention to our change in t. From 0 to 2, t changes by 2 units. From 2 to 3, t changes by 1 unit. So we could come out and do this work on the side, or we could write it in the equation. But if I do this on the side, remember that for my trapezoid, that I'm going to have a base, or I'm going to have two bases. I'm going to add them, divide by 2, so it's like the average of the bases, and delta t is my height. So I'm going to need r of 0 plus r of 2 times 1/2, or divided by 2, and then times my delta t of 2. That's my first trapezoid. My second starts here and goes from 2 to 3. So I'm going to add to that r of 2 plus r of 3 in parentheses, because I'm going to multiply that sum by 1/2, and I'm going to show that I'm multiplying by my change in t, which is 1. So if we carry that out, I've got to go back up to the table to see what those were. 2.1, negative 1.3, and negative 0.2. Okay, so we've got 2.1 plus negative 1.3 times 1/2 times 2. Well, the 2 and the 1/2 could cancel each other out there. And then we're adding to that negative 1.3 plus negative 0.2. Okay, so we should get 0.8. And then when we do negative 1.3 plus negative 1.2, that is, oh, and you know what? I forgot my 1/2 here, sorry. So times 1/2 times 1, and the 1/2 and the 1 are just 1/2. So that would be plus a negative 1.5 times 1/2. So 0.8 plus negative 0.75, which is a positive 0.05. Okay, so that's just the trapezoidal part of my approximation. So if I come back to this equation, T of 3 is 72 degrees plus 0.05 degrees. So I should use approximately here, but it's not a big deal. So 72.05 degrees Fahrenheit. Don't forget Fahrenheit.